A very good afternoon to you all, and you're all very welcome to this Saturday's CNPS technical session, presented by me, as usual, Ian Cowan. So this week we are completing a three-part series of videos which have been assembled by John Hodge on his Scalar theory of everything, or STOE for short. So we've dealt with some specific problems in physics, which are ostensibly addressed by STOE. So today in our wrap-up session, we are proposing to deal with problems. So it's basically a discussion of the problems yet to be included or solved, if you wish, and opportunities for research in the STOE. And as I say, this is the final wrap-up session of a three-part series, the two previous parts of which are recorded on YouTube, as usual. So John actually has informed me that he's engaged in some research on some of these problems, and I think over the next couple of months, he's concentrating on those problems, and we may hopefully have some further updates in due course. Now, let me see. So with your patience, this always takes a moment or two. I have to get the video up and I have to share it. So let me try to do that. If you just excuse me for a moment or two, I have to get that up. It's a bit slow coming up.
This video is about various types.
Okay. Right. All I have to do is... The video is up now. All I have to do is share my screen. So again, just a moment or two of your forbearance. And as usual, after the video has completed, we'll address any of the specific questions you have in the chat box. So if you're merely chatting between yourselves, which is fine, you know, that's excellent. But if you have a specific question that you want us to address, and John, as usual, is in attendance, please say this is a specific question so we don't miss it. And then we'll engage in a fuller discussion with the members of the green room. I see a few people have logged in now. So let's see, can we present this? The best way, I think, was to share my screen. Let me see now. Present, share screen. Select a tab to share entire screen. Right. Share. Now, I think what I'll do this time is I'll bring myself down, which means that if there's any specific intervention required, it'll take a moment or two for me to come back. So do please bear with me.
So, Ian, are you there? I need to break the. Ian, are you there? I need to break the. So the problem is that we're not hearing the audio. When you share the presentation, you need to share the audio.
Well, yeah. Thank you, Franklin. I very stupidly, the last two times I actually stopped the video and said, "Can everybody hear that?" And I think John at least said it's fine. So I assumed everything was all right this time. Okay. Well, I don't know what's happened. Do you know why the audio? The only difference, yeah, actually, I think maybe this is it. The last time I kept myself up, so my audio was live. So this time I didn't. That's a difference. Now, I think let's just see. Does this work? If I go back to it, I'll keep myself up this time. Let me see now where it is.
And there's the paper.
So I assume it's all right now that you can hear it. Can you, Franklin, or anybody else? Did you hear that?
Yes, go ahead and play it.
Oh, okay, so that's fine. Okay, so the question now is, shall I go back to the beginning?
Do not go back. No, do not.
I'm sorry about that, John. The mistake I made was to bring myself down, which meant that my audio was mute, and therefore, since everything was projected through my screen, there was no sound. I am minded to go back to the beginning again. What do you think?
No,
you see, it required somebody like Franklin with administrative functions to tell me this. So I'm glad you were here. So shall I go back to the beginning and start again? Let's do that. Let's, because it's been very interesting. I mean, I've heard it, but nobody else has.
Do not go back to the beginning.
Why?
Do not go back to the beginning.
Why? No reason. You must give a reason, sir.
Everyone has already read it. We just would like to hear the audio going forward.
We'll waste 20 minutes of the discussion time, but I think it's probably valuable. John, what do you think? I'm minded to go back to the beginning again. Franklin doesn't want to. James Keane has asked for the floor. James, what do you say?
John is one of our most brilliant. To the beginning.
You're breaking up.
Here's a person doing original experiments. This is very important. We want to hear John with the sound.
Yeah.
That's my opinion.
Okay. So does anybody apart from Franklin? Does anybody apart from Franklin object to my going back to the beginning again? No. So I'll go back, Franklin, if you forgive me.
It will just be a waste of time. We will have to just, because everyone has already seen that part of the presentation.
John, no, but they haven't heard the commentary.
It's usually just reading word for word on the presentation, so I just don't think it adds that much. So once again, John, were you able to? I mean, we'll do what you want to do, John. So do you want to go back to the beginning, John?
Well, I don't know. The first part really is word for word, as you say. I don't think you need any more than that. It's the second part that begins with the del B equals gravity that is perhaps a little more dependent on the audio.
Okay, so let's compromise. I'll go back to that mathematical part. I'll play it from there. That's probably only going back about 5 minutes. I'll not go back to the beginning. So that's a compromise, okay? Okay. Fine. I'll do that now. Find out where it is. Okay. Okay. It's only 12 minutes in. I'm starting now again.
Characteristics and back to direct the photon. Quantum locality says this experiment effect is not possible. Therefore, quantum locality is questionable. The second topic is that the gradient of the magnetic field in Gauss's law and Maxwell's equations is equal to zero. That is to say, there are no magnetic monopoles, and if you integrate over the surface, you end up with no net outward flow. What the STOE suggests is that what comes out from that surface is essentially gravity. That is to say, an attractive force to these Hodge, which are north and south poles of a magnet. These experiments, which I've done, and you can look up here, suggest that Maxwell's equations are slightly wrong and suggest that there are two different types of magnetic field: electromagnetic field, and a permanent magnet field. Part 5 of a series of 5 papers looking at the repulsion force between north and north poles and south poles has a slight asymmetry. As noted here, this is the summary of it. That asymmetry is gravity. So, following flux lines, this side of my Hodge, here represented as a horizontal line, represents the flux lines, but weak, that is, say, a small number of flux lines compared to the stronger side, which requires additional flux lines, which cannot come from the other side of the magnet. And therefore, these flux lines are then attractive, which turns out in the plenum to be gravity. The STOE model is that plenum is a magnetic field. The magnetic field is the only force field that's present. Electric effects are vortices in the plenum, and there's the paper where you can see it. This also suggests that the weak and strong nuclear forces are ad hoc additions to account for the supposed electrical repulsion of nucleons. If the nucleons are magnetic, they don't need to have some kind of repulsion effect. That is, the weak and strong nuclear forces don't exist. So here's how it works. If you have a distribution of Hodge, these each are going to have some effect on a surface area around the Hodge. You'll note that very close into the Hodge, that attractive force need not be necessarily spherical. But the STOE suggests the plenum obeys the heat equation, which means the plenum density flows from higher to lower points, but is never less than zero, even perpendicular, such as right here, to the radial direction. After a while, or some distance from the Hodge, the vector perpendicular to the direction of the radius from the center of mass goes to zero, because that's what the heat equation tells it to do. And therefore, you end up with a equal potential surface, which is spherical. This then is the spherical principle. It comes from the heat equation. There's no rebound that inertia would cause as in a wave, but the heat equation is necessary to have the spherical principle, which yields E to a real exponent, or the 1 over R factors. The moving Hodge produce first a decline, then move so that the plenum density at distant points appears to decline, then rise as Hodge pass and rotate. The distinction is also found in standard physics. The point particle concept is so the spherical principle, then the heat equation, may apply rather than the dipole, quadrupole, or Fourier equation needed. So point particles, which are quite possible, derive from a need to have the spherical principle. But the heat equation can be described by the Fourier series. The universal equation that I use uses only the first cosine term. With the gradient of the magnetic field being gravity and the previously mentioned experiments that I've done, the Maxwell's equation should be redone. The new version should reflect magnetic dominance, two different magnetic fields, and should include gravity. So, if the gradient of the magnetic field in the plenum is equal to the number of Hodge in the spherical surface radius at a sufficient radius for a spherical surface approximation, and Hodge produce gravity, the number of Hodge determine the gravitational potential. This is why the Newtonian spherical principle applies to gravity, and of course all those other places where point particles are theorized. This is the link between Maxwell's equations and Newtonian force equation. It applies to distances which are greater than the atomic radius. That is to say, for instance, it suggests the Casimir force is magnetic. So inverse square law of force is questioned for subatomic particles. Alpha, the fine structure constant, was detected by a slight separation of spectral lines thought to be because of electrons with different spins in an atomic shell. The Bohr model of orbits and relativity, which included a pure number alpha, and alpha here was calculated like this, based on the idea of electron orbits and momentum and energy in electron orbits. The alpha, the fine structure constant, is found in many different experiments. The spectra of atoms is the energy of emitted or absorbed light. Accepted physics hold that light is a wave, so the energy is Planck's constant times the wave frequency and has a speed c as a constant. Spectra being discrete lines suggests the spectral light waves are discrete. The Bohr atom combined with quantized energy yielded the Rydberg constant, which agreed in form with the formula found by Balmer in his Balmer series. But the STOE rejects a constant c, because c depends upon the plenum density. It rejects the Bohr model because electrons don't orbit. And the reason they don't orbit is because there's no emitted radiation, so the Bohr model is falsified. It rejects light as a wave. Light is fundamentally a particle. And it rejects Planck's law that energy is proportional to the frequency and the de Broglie wave particle equivalence, as we talked about earlier. But accepts that the Planck constant from the photoelectric experiment is the discrete unit of energy of the Hodge. The fine structure constant, describing the spectra as an orbital angular minimum characteristic of electrons, became untenable because radiation should be emitted. Later attempts became weirder, more complex, using quantum mechanics. The fine structure constant, the speed of light, is dependent on the plenum characteristics of magnetic permeability and electric constant. Planck's constant is a relation of energy to frequency, traditionally, which the STOE relates to the number of Hodge in a body needed to form light interference. And here's a paper to look at that. Electric charge measured in coulombs, the numerator of alpha, in the DeSangro experiment and others measured the speed of the Coulomb field to be much greater than the speed of light, and there's the reference for it. Speeds of light or less are of real bodies in the STOE because the body is made of Hodge. Speeds much greater than the speed of light in the STOE implies the thing is of a plenum. The Coulomb field, therefore, is a plenum field. Here then is a model of electrons and photons using disk magnets to represent Hodge. So here we show the net north poles. South poles are opposite that, of course. Top corner, bottom corner for the South Pole. And this then would be the direction of motion as the electron travels through a plenum. In the photon, there's the direction of motion, and of course there's one north-south axis. The same for the arrows indicate the orientation of the relative direction of movement. Constant implies no spin, no spallation perpendicular to the current. This is the electron traveling through an inhomogeneous field, which is the Stern-Gerlach experiment. And you can see the electron rotates about one axis of the North Pole and then about another axis, which gives its half spin or 720-degree rotation. And therefore, the spin measure is a result of magnetic poles and the direction of movement, not to the rotational motion, because the electron is held by its motion. In the structure of the electron in an orbit, what you have is here's two electrons, and there's a connection to the nucleus by a photon, which is a column of Hodge. And you'll note that when you do this, there's a natural angle that comes here. But the STOE doesn't have orbits or spins. The fine structure constant, the magnetic permeability, and the electric constants are characteristics of the plenum. The magnetic permeability is inversely proportional to the viscosity, or its inverse is viscosity. So in analogy to waves in a medium, we have the speed of light squared is inversely proportional to the permeability divided by the electric constant. And so all of these constants vary with plenum density. Matter is the emergence of Hodge and the plenum, wherein the Hodge capture and hold the amount of plenum between Hodge. The plenum density environment controls the spacing of the Hodge. Closer to sources has less spacing. So alpha is the amount of plenum captured by a single Hodge. You note the various constants, the electric and the constants are all related to the plenum, whereas the Planck's constant is related to the Hodge. So alpha is the amount of plenum captured by a single Hodge. It shows in equations that want to relate the number of Hodge to plenum forces. So this is the reason for finding alpha in so many places. Whether alpha varied has been studied with no change verified, but according to the STOE, the studies look in the wrong places. Distant quasars, local nuclear plants, etc. The STOE postulates all constants change and are dependent on the plenum density. According to very high rho near the sources and at the center of spiral galaxies, we expect to see the alpha change, or in very low rho between galaxy clusters, we expect to see galaxy change, and therefore there should be no carbon very close to the sources, and further out there should be no atoms. Is the alpha dimensionless? It depends on what charge and Coulomb mean in the plenum, and the units of the plenum, which are so far defined. Certainly, the count of Hodge is a unit of measure that is not usually considered in dimensional analysis. So we need a few more measures or standards, such as the count of Hodge and whatever plenum density means, to be included in our units of measure. The STOE is a holistic emergent model. So the basic units of measure should be the plenum density, such as the magnetic constant and electric constant, the count of Hodge and Hodge characteristics, such as its relation to gravity, which, as we saw before, is the count times the gradient of the magnetic field, or its relation to magnetic strength. From the photoelectric effect experiment, the epsilon is proportional to the number of Hodge in a photon, where you add one more Hodge, and that then is the slope of Planck's constant. What are emitted photons? Here you see that diagram I showed you before. This is a photon going to the nucleus. Here are photons going between electrons in an orbit, and there may be photons going out from here, which may connect to other atoms. The stable angles, you see, these stable angles are produced here vary such that one extreme would suggest a circle of 8 electrons, the other extreme would suggest a circle of 18 electrons, and these are magic numbers in the periodic table. The model with the spectrophotons being the links between electron leads to geometry and to the larger nucleus magnetic strength, making different radii, length of neutrons to the electron photon. So perhaps the other electrons can also be stable geometric links rather than a surface around a nucleus and rather than in orbits. Friction. In classical, friction is treated as a heat ability to do work, which is a loss, a dissipation of energy, or a force causing dissipation. It seems akin to entropy, yet the Lagrangian and Hamiltonian equations in traditional big and small physics ignore the dissipation of energy. So the issue becomes how to integrate dissipative forces into the STOE. Hodge are suggested to be two-dimensional magnets. If friction is a macro effect, the movement of Hodge is without energy dissipation. I asked on a research gate about the cause of friction in the quantum realm. Emmanuel here answered it was caused by something emitted. Well, in the STOE, this something could be Hodge. I had already done something like this previously in looking at redshift and the scalar potential model of this pioneer anomaly. Both of them had photons, Hodge, being emitted from photons as they traveled through space. The photons were considered stripped by means of spallation of Hodge by the plenum force as the photons traveled through space. But where did the photons go? They become part of the background temperature as observed from Earth. And here's a paper where we look at the cosmic microwave background radiation dependent on source and sink of the galaxies. Wave equation versus heat equation. In the universal equation in the scalar theory of everything, the rho at a given point, which then determines what the forces are on the Hodge, is dependent on two different types of reaction. One you see here. This then is inversely proportional to R, which is a heat equation derived structure. The other, and here you see the heat equation term from a mass, but this also has a cosine term, which indicates a wave equation. So the problem is, does this wave equation hold, or is it totally a heat equation? Of course, the rho at a given point then determines the force on a given Hodge. The first two terms of force presume the heat equation, and of course that derives the 1/r relationship. The heat capacity of the medium and a density usually electric constant and rho, where speeds are like that we saw before. Has the advantage that heat processes are irreversible without heat input. This leads then into friction and entropy. Was used to calculate the CMB temperature, that is to say the heat equation was used to calculate the CMB temperature. in the microwave background temperature. The heat equation results in a spherical principle, which is inverse distance of density and exerted on the surface of the hod. This is what Newton called weight. See structure later on. The heat equation is actually very important in physics. It gives the inverse distance squared force and the idea of a point source. Let us say when R goes to 0 and somebody says, well, gee, it's got exponential decay. It has a heat equation. That's why they say particles are point sources, is because they want to have this spherical principle in their ability to represent fields. Yet, the advantage of the heat equation is it allows the plenum to have inertia to support wave action. So that's it, spherical principle versus inertia in the plenum. The third term, that is, say, the mass term, has actually in it the wave equation solution, the cosine term, which suggests the propagation of plenum density has inertia and no dispersive friction in the plenum. See, so it's Hodge that are dispersed to cause friction. Because the second derivative with respect to distance must exist, the Fourier series of the heat equation may be used as an approximation. Is there one evolution equation which has a turning point, such as the area equation? I don't know what it is, but I don't think that there is, where the third term is a solution. Such a situation is also suggested by the magnetic pole repelling experiments, where we looked at inverse distance cubed, and inverse distance squared further away from a magnet. Or the Hodge may vibrate as they move from high rho to one side to rho on equal to 0 on the other side, so they're sitting there vibrating in the plenum, and you have high, low, and it's this kind of high-low switching that then provides the illusion of a wave, the cosine term. But the issue of where does inertia reside remains. So plenum is heat equation, and inertia is a resistance, a force a hot experience as it tries to move along its axis. But what keeps it moving then? Open question. Entropy. The observed characteristics of the universe is that actions occur wherein some of the energy that was initially present is lost. That's the energy comes in through the source and it's eventually lost out the sink, and in between it declines. It cannot do additional work. The lost energy is called entropy. It has become known as an increase of disorder in isolated systems called spontaneous action. That is to say, there's no external heat or sink inside the so-called system, and the system disorder increases. But what about crystal formation? From disorder, which involves heat release. So here's a system of disordered atoms, molecules, and suddenly they start forming crystals and heat is released from this. This is contrary to the idea of an increase in disorder. So entropy in the STOE is heat release that cannot be recovered, and that covered both situations here, from sources to sinks, heat release from sources to sinks. The energy is Planck's constant times the number of Hodge, or Boltzmann's constant times the absolute temperature. Therefore, in the STOE, the entities lost are Hodge, as we saw before. The plenum is related to the amount of plenum that accompanies the captured Hodge. So here is the STOE universe. We have a source galaxy, a sink galaxy, and these things form galaxy clusters. The source emits Hodge and plenum, which form hydrogen. Hydrogen travels out from the center of galaxies form suns, and some of the suns travel inward by gravity to form nova, and then some parts of the nova continue on and become black holes, which then go back into near the source and are evaporated by the extreme plenum density. Some of the nova elements travel outward as heavier elements, some go back into the sun. So what travels to the sink is these heavier elements, hydrogen, and of course, light and Hodge. As this heavy stuff with hydrogen travels toward the elliptical galaxies, it gains a lot of energy, and so around sink galaxies, you have a cooling flow to cool things down. There are several differences between sources and sink galaxies, and that's covered here. This then is our view of a galaxy cluster. You then have spiral galaxies all emitting the stuff of the universe, and as the stuff is emitted, some of it forms elliptical galaxies, which then cause the plenum density gradient to direct the stuff of the universe back into elliptical galaxies. So the universe entropy must include a dissipative term, which the standard models do not, and it views that generally the arrow of time is in this direction, but you'll notice this loop here, so this is the arrow of time sometimes, but in the end, the stuff either goes out to sink galaxies, this arrow of time goes back to the source and then back out again. The structure, and this is the structure of subatomic particles. It suggests this building block of the Hodge, which can be modeled, or we model it as, the analog of a disk magnet. So we use disk magnets in our scale as a fractal or self-similar analog of the subatomic scales. The structures bodies cause the observed behavior. So look for stable geometric structures of disk magnets. Unstable structures produce short lifetimes or antiparticles. A prior paper suggested structure of the photon, neutrino, and electron. That's it. So this is the photon, is a column of Hodge or column of disk magnets. You'll notice that in the direction it travels, these things are zero-dimensional, so there's no force exerted on a photon traveling in this direction. The same thing is true of a neutrino. There is no force when they travel perpendicular to the paper here because there's no surface area presented. And that is what the toy simulation did using this structure and its interaction with the plenum that produced the toy computer simulation model for the diffraction and interference effects, which is worked in even situations that reject the wave models of light, such as the transparent mask Hodge experiment. This is the structure of the electron as we see it, which is a very stable structure. And you know we've outlined the North Pole. So you got one North Pole, top to South Pole on the bottom, and of course the same kind of thing for 4 North Poles. The minimum surface area, you see here's a big surface area and here's no surface area. So the minimum surface area is going to be somewhat in this direction. And the electron is going to be held by its motion to try to be in that direction. This view of the nucleus was suggested by Emmanuel, and you see it's ball magnets forming a proton. This part then would be a proton with electron, which is a neutron, and here's your column of Hodge. The advantage is the north-south axis is tangent, north-south axis of the proton. Its surface, and that means that the magnetic strength going this way is inverse cube distance, like the strong force, and it allows a column of Hodge, a photon, to attach magnetically. The STOE accepts holism, emergence, and anthropic principles. That is to say, if something exists, it must be able to exist. So Hodge become photons with diffraction, which become electrons with the Stern-Gerlach results. Diffraction including the Hodge experiment of transparent mass, which reject all other models that I'm familiar with of light. This seems possible with a rigid flat structure for a magnet, a disk rather than a sphere or a ball magnet. So here you got electrons, photons going to the nucleus, also photons going out to perhaps other structures to provide chemical links, and photons between the electrons, which eventually are emitted when you start emitting spectral lines. So how can photons connect electrons to form what amounts to subatomic particles? Well, you can continue out on either side, here horizontal or perpendicular, with magnets to form long photons, which then connect to other electrons. They can connect in two different ways, either straight across or at an angle. So these can be, you can see here, there's two magnets here. They can be neutrinos connecting. Here's what the structure would look like for a two-electron structure with connecting photons. There's two ways to connect, as you can see here. With photons connection, if there are two types of structures with different charge, that means there's 8 types of 3-electron structures with different charges and magnetic reactions to magnetic fields.
Right. I'll get back to the ordinary situation by stopping the sharing of the screen. Now, you'll have to bear with me again because I've concentrated on the video and I haven't been looking at the questions coming in. So I'll just spend a brief moment looking at those. Evidently, the recording will show all the lines in the video without the audio until we corrected that error. I'd like to thank Franklin for bringing that to my attention. But unfortunately, the recording won't have the audio for all time, which would have been nice. Anyway, let's see what are the questions coming in. Because John actually has been answering a number of questions in the past, and I dare say he's done the same now. How's the plenum different from the ether? Yeah, so Quest asks, I forget, how is the plenum different from the ether? I think John has addressed that here. Not difficult. No, he's just saying how he created the video. Let me see. Okay. And my apologies again. I really didn't see that message from Franklin coming in at an earlier stage. My screen was maximized and I had my full attention there. But anyway, James is asking Aratune whether there's supposed to be sound. Okay. Sound. Yeah. I'm sorry. I didn't see that. Didn't see it until you physically intervened. Thank you for that. And you're coming down. That's right. I wasn't looking at the chat room. That's correct.
Yeah, we've got some questions. I'll just pick some while you're looking through. But we can bring up John here. So, Quest is asking, so is a plenum essentially a magnetic field? And then, like, the other question was, is the plenum basically the ether?
The idea of the plenum is along the lines of an ether with a different name because it has a different property. The plenum in the STOE model has no particles. Many ether models, as you know, have considered the ether to be particles. That's not true with the plenum. That's why I use the word plenum. But basically, the magnetic field is a field of the plenum. Meaning what a Hodge is a magnet on the north side that is one side, which has a very high plenum density. And on the other side has a very low plenum density. And the mismatch between those strengths turns out to be, when you get at greater distances in the atomic scale, to be gravity. At less than atomic scale, of course, it's magnetic field, not gravity.
So I guess someone might be confused, because I think a lot of people are thinking your plenum isn't ether, but you say it's no particles. But then you say that there's a density difference between the north and the south. And if your plenum has no particles, then that kind of contradicts the whole density definition, doesn't it? Density is like particles per cubic centimeter, and if it's higher, it's higher density. So how can you say that your plenum has no particles but yet has a density property?
Well, to say that the ether has particles is not a universal truth. Many people, or some people, few perhaps, accept that the ether does not have particles. This is just, we're talking about fundamentals here. And
yes,
fundamental
that if it doesn't have particles, then I would assert it cannot have density, or what you're calling density.
Well, that's your model. Mine is it can have density.
And
well,
logically, how can it have density?
It's very simple. You calculate it. The whole first part, actually, and maybe we should have gone over it again, but the whole first part was the existence, the reality of the plenum, which is the same kind of question of the reality of the ether. Right? The question whether or not the ether exists. So we have an experiment that suggests that the plenum is real, but it can't have particles. And that's just the fundamental of the STOE. We start with postulates, and then we take those postulates and see how far we can go to explain experiments. And that's what's going on here. And one of the postulates is the plenum exists, it's real, ontologically real, and it has no particles. It's a continuous medium without particles.
Getting back to a very elementary level, you're talking about Hodge a lot. Now, some people may be a bit confused. How would you give a brief definition of a Hodge?
A Hodge is a magnet, right? It's a two-dimensional surface area, not a point particle, a two-dimensional surface area, and it has high plenum density on one side and low plenum density on the other. And what happens?
Particle.
Say again?
Is your Hodge a particle? Because I was confused about that. I didn't know whether, because you have your plenum, but if you have Hodge, then that could
The
certainly,
Hodge,
I don't know.
yeah, the Hodge is a particle, yes. And when Hodge, along with the magnetic field, like magnets, combine, they form particles. So every particle we know, the baryonic matter, is some form of construction of Hodge. And that's the divider. Hodge travel at the speed of light. The plenum wave travels at many times the speed of light. So first you look at how fast a force travels, and that determines whether it's a particle or whether it's a wave.
So you yourself, Franklin, have asked this, but I think it should be, if gravity was so strongly related to magnetism, is that what you mean? Then all gravitational bodies would have measurable magnetic fields. This is false. How would you address that, John?
Well, bodies are made up of electrons and protons, and they have magnetic fields.
Not necessarily. My points further in the comments was that magnetic fields clearly only exist in charged particles which are in motion. And some of the other comments was that it's kind of hard to tell whether an electron itself, we say it has a magnetic moment, but does it really have like the north and south pole and a fixed axis? Because the moment you put an electron inside a magnetic field, it's going to deflect. Now that could have been because it's a small magnet, or it could have been that it's just obeying, Lorentz force law, and that's just what it fundamentally does, but may not actually contain any findable north or south pole. And but I think my comment there was still kind of in a misunderstanding that you're saying that the gravity is like the curl dot magnetic field. So a magnetic field must be present. And generally speaking, when we're talking about atomic matter, all these positive and negative charges are all balanced and stationary, which generally produce no magnetic field at all. So once again, it's kind of hard to tell. If you have say a uranium atom, big atom, whether you can find a distinct north and south pole on that thing. And I think what experiments we do have show things like, there's some magnetic moments. If you put it in magnetic fields, it may twist and has torque, and we can measure certain magnetic properties on that atom. Once again, that is a difference between it reacting to magnetic fields versus it being actually a magnet. Like if you took two uranium atoms, would the north pole of the uranium atom attract the south pole of the other uranium atom? And I'm just questioning whether that actually happens, because like I said, I don't think that the individual atom necessarily is a magnet. The other problem is that what is a magnetic field? I mean, what defines the difference between space with very low magnetic field and space that's right next to a neodymium magnet that's very strong? I'd be curious for you to explain. Well, what is the physical difference there?
Well, you've gone over.
Could you explain that, maybe, John, and then maybe we'll stop this particular point, Franklin, because we have to move on. So, John.
Well, Franklin is dealing, in my opinion, correct me if I'm wrong, but you're taking what currently exists as the model, and you're saying an electron is a charge, and therefore you got to have a charge that's moving. But that's the model. That's not necessarily an observed fact. So if you then take the reverse and you say the electron is in some kind of magnet and it moves and it produces a charge, why not? Now, the problem is the Stern-Gerlach experiment, in that if you think of the Stern-Gerlach experiment, an electron going through it, and consider it to be magnetic in nature, not electrical in nature. So you don't need rotating charges. I mean, that's been the bugaboo of what an electron is for decades, is they've got to have a magnetic moment, so they consider it rotating charges or moving charges or something like that, or toroid of charges. I mean, all these kind of models. But consider the Stern-Gerlach experiment. If you have an electron, and one electron is not one magnetic north-south pole, but 4 magnetic north-south poles, you see? And so when it then goes through or travels along through a inhomogeneous magnetic field, the Stern-Gerlach experiment, it's going to orient in one of 2 ways. The magnet itself, the electron itself, the magnet, is going to orient along one of the north-south poles or another one, and it's going to create the 2 dots. Now, the other experiment is that one I did with the boy at Scalar Law. That's why I did that experiment. You know, it was a wire and put a magnet there and see what happens. What you get is forces directed perpendicular to the wire, not by a Scalar kind of law. And that is done because the electrons are traveling in a given orientation all the time. They don't rotate. There's no spin in electrons. There's magnetic fields. And the spin of an electron is really 4 magnetic fields of the electron.
Okay, I mean, I see there is a fundamental difference in the conceptions of you two gentlemen. And that's fine, because there have been other points expressed which I was very interested. So,
Yeah, we still have plenty of other comments, so I was hoping to give you a chance, Ian, to pick out a few more while we were discussing this.
very good. Thank you, Franklin. You've gone on a bit more about this, so maybe I'll just skip those comments and get on.
But we see some other interesting. Questal has a bunch of questions here.
He does.
Address this one. How to combine the nuclear force with other forces, or instead of that, the electric force specifically? And I guess it's a question about how do you see the fundamental forces in your theory?
There is only one force in the STOE. I mean, that's what we're ending up proposing here. And that is the gradient of the plenum. Okay. And that force, depending on the circumstances, emerges to become the other forces. Okay. So it emerges to become gravity, as we covered in this video and another one before. It doesn't need the strong and the weak nuclear forces at all, because the protons and neutrons are magnetic and they're held together magnetically, and so too with all the other particles, subatomic particles. In scales less than the atomic scale, it's primarily magnets. You see, the trouble is, when I say emerge, I mean that if you get the scales larger than the atomic scale, you end up with, well, what we now call gravity.
There's a very fundamental. There's a very fundamental question here, maybe a simple question. Robert K. is asking, are you proposing a quantum theory of gravity? Would you say yes or no?
No. No.
Right, that's it.
You understand, in the STOE, and this is one of my personal, when I was in grad school, I got a C in quantum mechanics, right? I mean, you don't get C's in grad school, supposedly. But man, I just could not get quantum. But based on that, you understand, I don't accept quantum at all. That's why we did the invariance experiments the way we did them, is to take the basis of quantum mechanics, which is the interference experiment, and say, look, you know, it doesn't work according to quantum. It's a straight classical kind of experiment. So I'm not doing quantum anything.
Okay, well, that's quite clear.
I mean, here's an
So I let
interesting
my-
question. This is to Shockwave, but there's this whole question about, say, the electric force. So, is the electric force also an aspect of the plenum? You're saying, how does the electric force arise, and how do you explain? Say you have a positive charge and a negative charge. So, what causes those to actually be pushed together? Or if you have two positive charges, what actually causes them to run away from each other just spontaneously?
Well, we start with considering that electric characteristics experiments start with the movement of magnets. And what that is a plenum producing vortices in the plenum. So electron moves, and because of the shape of the electron, it creates a vortice in the plenum, whether it be a kind of a tornado type or a ring type vortice, is whether it's a positive or a negative charge. Now, vortices have a funny characteristic in that the same type of vortices tend to repel each other. They tend to go away. And they go away at very fast speeds, meaning many times the speed of light. That's the DeSangro experiments and some of the other people who've done experiments like that. So the electric force, the vortices, have to be plenum in the STOE because they travel at a speed of much greater than the speed of light, you see. Now, don't confuse then in the STOE the electromagnetic signals. Electromagnetic signals are individual Hodge being thrown out from a wire. And they are these little magnets, these Hodge magnets traveling, and they travel at the speed of light. You see, I don't know if I'm
And when you talk about exceeding the speed of light, you don't mean 1.3 times the speed of light or 1.03.
No.
You mean powers, orders of magnitude greater.
Oh yeah, 10 million at least.
Yeah. Okay. Cornelis has just said. He says, if I am correct, the plenum would have no density, as it is a bound field only and is synonymous with ether. It would be the energy density in the plenum ether that varies. Do you think that's correct?
Well, I'm not too sure what he's getting to here. He wants to call it an energy density. And I don't know. I've thought about that for a good long time. And I'm not too sure how to answer that.
Rather than a density. We might bring him in later to talk further
I consider
on.
The plenum has a density, but it can also be captured by a Hodge. So remember the conversation there about the fine structure constant was a ratio of how much plenum is captured by a Hodge. But that's not all the plenum there is. The rest of the plenum is just regular density. Now, in the photoelectric effect, you have a slope of a line, right? And here the energy, I don't like this kind of terminology, but the energy then is proportional to the Planck's constant times, frequency is the way it was presented. But the slope of a line, if you add, if a photon, which is where they talk about frequency, and that's another subject, but the energy of a photon is the number of Hodge in the photon. So if you add one Hodge, you increase the energy by Planck's constant. You see? So the photoelectric energy is number of Hodge times Planck's constant. But plenum density, as far as energy goes, the plenum comes from sources, sinks, and all matter in the universe. And with that, if you remember earlier, I had a formula there where you calculate just what the plenum density is at any given point. Let's see. That's an energy density. It's a density. I'm not too sure it's an energy. I mean, I get kind of antsy when you talk about plenum having an energy density. I don't know.
Okay, gentlemen, there are a number of other questions there related to this and other issues, but time is running out, and I'd like to give an opportunity for people in the green room to express their views. And if we have some more time, we can, of course, come back to these points, if that's agreeable to you. So anybody in the green room that would like to make any specific point before I call upon you? I see Harry was there a moment ago, but he's disappeared. I'm not quite sure what that is. And Dennis said that he's having computer problems. But Jim, would you like to give some reaction or any specific query about the validity of this or the conception of this to John?
Well, thus far, I think that John has done some brilliant experiments and has produced some data, not some of it presented today, with the nail and the slip experiment and so forth, which are actually consistent with binary mechanics. I must admit that John's theoretical explanations for his own data and in the STOE theory is I haven't really fully grasped it. Like for example, why is a Hodge a two-dimensional object? Don't we live in a three-dimensional world?
Sorry, just housekeeping matter. We're getting a bit of high frequency noise coming in. I don't know. Perhaps somebody needs to mute his mic. Who's not speaking. Sorry. Go ahead, John.
The idea of what a force is, when you take a look at Newton, is the gradient of the plenum against a surface. The Hodge is a surface. The problem that we have to face here is photons, light. Light travels at a speed which is dependent on the plenum density, but it's the maximum speed that any particle can travel. This is the Lorentz idea, not the Einstein idea. And it must be able to travel at that maximum speed for all plenum densities. So in the direction of travel, a Hodge or a photon cannot have any surface area. Therefore,
cannot have any surface area. Well, doesn't a two-dimensional object have surface area? You see, yes. Like I'm trying to understand what you're saying here.
Could you maybe visualize that for us, John?
Trying to get to something to visualize it with, but.
And then, of course, other related. Oh, go ahead, John.
You see, that has very little surface area in that direction, but all kinds of surface area in that direction. So the force, the surface area is directed normal to the Hodge, axially along the Hodge. But in the direction of movement, this is the way with no force being directed, allows to travel at the fastest speed possible.
Oh, okay. So we're talking about a two-dimensional surface. Oh, okay, great.
Now, there is another.
Do you tell us what the size of a basic Hodge is? In meters, or the area of its surface in square meters, or do we know what the size of these things are?
I have no experiment that says that, but I have thought that it roughly must be along the lines of a Planck length.
Must be along the lines of what?
The Planck length.
Planck length.
Yeah, the diameter
Oh
of the
my
Hodge must.
goodness gracious! That's well, in my book, the Planck length is a complete fiction because it is based upon constants which are unexplained measurements.
Well, it's not
So
even
the
based
Planck
on
length is another unexplained non-number. I mean, it gets you nowhere. You know, it's sort of like trying to master calculus when one has not yet mastered algebra, or trying to
well,
master algebra when one has not yet mastered arithmetic. Okay, let me ask another question just to sort of pick your brain and perhaps I'll better understand things. Is there such a thing as a volume of plenum, or this ether, which you're calling plenum, which has a constant density in that volume? Is that's sort of a yes or no question? Is that a possible thing to occur?
I suppose it could occur, but it's not likely.
Well, it's not likely. Oh, okay. Well,
I mean,
or we could just
you'd
say
need,
a very low gradient. Extremely negligible gradient. Then I ask, if you place a Hodge in this volume, this two-dimensional object, this Hodge, in this three-dimensional volume, and you state that one side has increased increased plenum density, and the other side of the Hodge has decreased plenum density, how does that Hodge change the plenum density?
the greater
I'm
than
trying to
atomic,
figure out whether we have circular thinking here.
at greater than atomic scales, remember one side of the Hodge is no plenum density right on the surface on one side, and high plenum density
Well,
on the other.
wait. I thought the Hodge was a two-dimensional object,
Yes,
a surface,
it is.
and
Yeah,
how so a plenum density would not apply to either side, would it? How
oh no,
could that be?
why shouldn't it? I mean,
Oh, so
it's
you're
a,
saying that placing a Hodge in a volume of plenum with negligible or near zero variation in plenum density, the Hodge causes a gradient of plenum density to then occur. Is that the line of thought?
that's right.
Oh, okay.
Okay, well,
I'm making progress. Sometimes you have to explain things, John, to me like I'm a 5-year-old, and then I get it. Okay, let's see. So we're not sure of the Hodge size. Like I don't buy this Planck length thing or the Planck time or any of those Planck values are just more unexplained things that we're not even ready for if we haven't even explained why light speed in vacuum measures what it does measure to be. And the other thing.
we're getting the interference back again. Perhaps I'll try to mute mics, except people speaking. I don't know if Franklin's. Yeah,
It's in
not his.
traditionally, so you're losing what I'm saying.
Yeah. Can you hear the interference as well, Jim?
No, I'm fine. I just paused because the little circles on the video disappeared and the little circular loading icon was appearing, and perhaps we're just sort of shut down during that momentary interruption in
Seems like an echo to me, actually.
So the units of Planck's constant H are energy times time. And yet you seem to be dropping you seem to be saying that you think that somehow Planck's constant is some kind of quantum of energy. That just doesn't make sense to me.
Doesn't make sense to me either.
Okay. Well, then why is this being asserted? One last question, and then perhaps Ian has other people who want to. I don't want to monopolize too much time
Yeah,
here.
thanks very much. Yes.
One last question might be: if a photon is thought to be some kind of a particulate, excuse me, some kind of a particle, how can it have a frequency in your line of thinking, sir?
I'm not too sure there's a short answer here.
Okay, well,
Okay,
I
let me
will
try
go
it.
back and watch your videos because I find your data and results are absolutely brilliant, and I thank you for that. I'm not sure I understand your theories, but the data you produce in the experiments are very imaginative and interesting, and I congratulate
thank
you
you.
on that. So
Well,
I'll
let
say
me try
goodbye
that.
and let other people talk.
Thank you,
Try
Jim.
it.
I think you've helped actually to clarify some of the concepts for a number of us, because it's frequently a good idea not to have merely the lecturer talking, but to have the students talk and maybe ask the lecturer questions and hence
Right.
clarify things. So thank you for that.
Especially a student like me where you have to explain things like I'm a 5-year-old. And
Well,
then I get
that just means that you're very exact and you want things specified very precisely, which is nothing to be condemned. Thank you, Jim.
thank you.
Now the other
Then
thing.
I would like to try his last question.
Okay,
Just for a little
if you
bit.
want to say something about that.
10 years ago, when I was looking at how to explain interference with a photon, what you have is a photon that travels and emits a wave, and it impacts other photons. But the wave that it ejects, like dipole antennas, ejects a particular, very unique kind of wave frequency, in the plenum. Now, what happens if you just take a bunch of photons, incoherent light, and just let them go? And what I did in the experiment, in the computer simulation, was just let the thing run with 60 photons in it and just let it run. And what happens is the photons start to line up in lines. And the distance between those lines is what is the de Broglie frequency. See, it's the number of those lines per unit distance. And they line up according to the energy of a photon, the number of Hodge. So the number of Hodge in a photon translates directly into the wave, the distance between these waves of photons. Now, well, okay, I think I should stop right there. Thank you.
Just a very, very small point of clarification on the analytical part of the video, John. When you were talking about it was really the divergence of the magnetic field vanishing and so on. I think you were talking about gradient, but it was really the divergence, of B.
Yeah.
Yeah. Okay.
Yeah, it's divergence because V is of X.
Okay.
Yeah, I talked about the gradient of the plenum density and the divergence of the magnetic field. Yeah.
Right. Okay, very good. Thank you. Now, Vladimir has given us a number of presentations on his own womb theory. And for my part, I think there has been some complementarity and, dare I say, conflict, essential conflict between your two theories. So would you permit me, John and Vladimir, to add Vladimir to the stage, just maybe briefly to get your reaction to today's expansion of the STOE theory, Vladimir, just what John was talking about today, these other problems, and how they might or might not relate to the womb theory. Maybe they're looking at the same things and trying to explain the same things, or maybe there's some fundamental conflicts, just very briefly.
Let me tell you very briefly. First of all, I try to understand this theory that is very far away from my knowledge, from my education, from my model. That's why it's very difficult to compare them. They're principally different theories, different models. But let me tell you, I do have a respect for any model, and far away even from the classical physics. I'm very happy to hear some different ideas that maybe somebody can use in his models. In my model, I used already all what I knew about the classical physics for 300 years at least. I finished it, and I don't see any interference between these two theories. It doesn't mean that it's wrong. No, it means that there is another way to explain our world we live in. That's why I do like to hear on our sessions different ideas, different models. Maybe some of them will be more efficient than mine, simple like this. That's why let's do all the new ideas. Let's talk about these new ideas. Let's discuss them as it was today. Maybe it will be something, useful for all of us. Thank you so much for your three talks. It was good, It was good that you presented them. You presented your ideas, your understanding of the world. It's so much different, but it's okay if it's a consistent. If it can explain some experiments you've done yourself, it's good for us.
And we might be able to be a bit eclectic, taking bits of theories from various authors and so on and putting them together. By the way, I've just found out, unfortunately, that it's John's mic which is giving this interference. When I mute you, I think it might be something on your line. But anyway, would you like to respond very briefly to what Vladimir says before we bring him down, John?
Well,
or do you agree?
Tend to agree.
Yeah, I thought that's good.
Not with his model, of course, like he disagrees with my model. But yeah, we got to talk about models, and that's the way science advances.
Oh, okay. Well, thank you. And Quest has made a comment here. He says, I think Vladimir simply acknowledges that John's theory is outside the scope of his own work. So thank you very much, Vladimir.
Okay.
If you want
Let's
to come in
continue with the different models. Let's continue your sessions.
Let's continue.
My suggestions.
Harry is here, and although he is not visible at the moment, and his mic is muted, but I'm wondering if he'd like to come up and just give us a brief response to John's points that he's raised today, these other problems, Harry.
I have a question. I'd like a specific explanation of how, a clear and specific explanation of how electromagnetic waves leave an antenna. And please be very detailed, because just saying that Hodge leave the wire is not really a description of how electromagnetic waves in an antenna works. And you can use a dipole if you wish.
So there's a problem, John.
What?
There's sort of a problem put to you, very specific. He says you're asking.
No.
Yeah.
This is the two experiments associated with the Biot-Savart law. It's very simple. The electrons, and you know what electrons are. They're these magnets, an assembly of magnets that are moving along, and they maintain a specific direction.
Excuse me, that's not what I asked. That's not what I asked. I'm asking electromagnetic waves. I'm not talking about the Biot-Savart law. I'm asking in an antenna, okay, that emits electromagnetic waves. We're talking at a high frequency. We're not talking about DC. Does that make sense to you? Not DC, AC waves. So you're saying that a photon is emitted by a dipole antenna. I heard you say that. I'd just like to know how that works.
You wanted to know how an electromagnetic wave is emitted from an antenna, which is a wire. We agreed with that. The antenna is a conductor, no? When you charge the conductor, you have a current going down a wire. You trigger the Biot-Savart law, which says that something is emitted. In the experiment, that something that is emitted perpendicular to the wire. It is not emitted like Ampere says it is, that is, say, emitted in all directions. But what is emitted is an electromagnetic wave. No, if the current is oscillating with some frequency, then the frequency of the emission is oscillating, and that's called an electromagnetic wave, is it not? But isn't that an electromagnetic signal? And what that is,
you haven't answered my question, so I'll just say that you don't have an answer yet. So let's just skip it.
Well, with respect, I mean, if we were to go into very great detail scientifically to give you an explanation of that, according to any theory, conventional, John's theories, my theories, we'd probably need a complete lecture in itself. So maybe that's something we could do for the future. But
well, first,
I'm not really happy with the idea that just a wire emits Hodge.
You're speaking together. We can't hear you.
This is acceptable.
I don't believe that the wire emits Hodge. I'm sorry.
You want the detailed explanation, or don't you?
Well, send me an email. Come up with an explanation. I don't believe that a wire emits Hodge. Sorry.
Well, if it's not possible to give a very simple explanation of this complex phenomenon, maybe you can give us some reference.
It's not that complex. I mean, you can go to any book on a ham radio book on antennas, and they'll give you a description of it. I just want to know how it works in his theory of Hodge.
Well, he's sort of talking about electrons, and you said you weren't interested in that. He
talks about electromagnetic waves, and yet I don't see an explanation.
So first he wants to hear about it, and then when he starts to hear about it, he turns it off. Great. Bad science.
You didn't answer my question. You started to answer something else.
You want to allow it or not?
You didn't understand my question. My question was very specific. In a dipole antenna that has an RF signal, tell me how a Hodge is emitted, and it causes the radiation pattern that's well known and well measured in textbooks, in radio engineering books. Explain that to me. I don't understand how what you say is possible.
So let's give John 5 minutes. We have the time to address that without interruption. Can we do that? John, the floor is yours.
Where we were, the Biot-Savart law. It's emitting something. It's emitting magnetic Hodge perpendicular to the wire, not at any angle, just straight perpendicular to the wire. And those Hodge, when they get together and go on out, are the electromagnetic wave. They're magnets, so they are moving, and therefore they have an electrical component. So the emission of those Hodge perpendicular to the wire is the electromagnetic signal that he wants. And that's proven and that's shown in the Biot-Savart law experiment.
Oh, okay. Now, I may have adverted to this briefly before, but John P. Wesley has looked at various things, and he contends that the Biot-Savart law is not general, and he questions its compliance with Newton's third law and the conservation of energy, and he goes back to the more fundamental Ampere force law. and talks about maybe BS of R or Grassman, which is equivalent, as being maybe not always the case. Have you any response to that? Do you agree or not agree, John? Or
I'm
are you
not
familiar
familiar
with
with
his work on this?
No,
Okay.
I'm not familiar with it.
Well, needless to say, I mean, I use BS of R law quite a bit. What does Franklin say about it here? BS of R law relates a current with the generation of a magnetic field. This has nothing to do with how a radio wave is generated. Well, that's possibly what Harry was getting at, but you don't agree. You think it is fundamental, and we'll have to accept that.
The radio wave is magnets moving.
Okay. Okay. Well. Okay. Okay. Well, we've had some conversation there. As I say, if we wanted a detailed explanation of any particular phenomenon according to a particular theory, we could devote a complete lecture to that. And I'd like you all to consider that. Maybe we'd have some volunteers. John, as I said, has been corresponding with me quite recently, and he's talked about some additional work he'll be doing over the next 6 to 8 weeks, I think it was. And if there are any interesting results that he thinks would be appropriate for us to address, he will bring those results to our attention. So we can look forward to that. And again, if anybody else wishes to volunteer to give any response to these ideas, we'd be welcome. They'd be all welcome. I mean, personally, I'm very interested. I hope I'm open to all the ideas, but I'm almost skeptical of sort of philosophico-physical ideas. Whatever they be, whether they be particulate or whether they be Hodge or whether they be magnets or whatever. So I'd like to listen to these and get a conception of these, but I'm almost very, very slow to accept them as being the basis of reality. So let's just see. We have maybe a couple of minutes left before we have to terminate the talk today, and just see. So Michael Sharia, I don't know if Sharia, I'm not pronouncing his name correctly. Much like John Hodge was talking about vortices, a magnetic field is like the top and bottom of the Earth, and the spin is the equatorial region where it approaches. Well, he's just making a statement there. So I don't know if you have any comment on that, John, good, bad, or indifferent. Franklin has come back to say, it's funny that they call a radio wave electromagnetic when no such magnetic or electric field has ever been experimentally measured in a radio wave. Well, I know that's if I may say, is a Franklin's hobby horse, and not everybody would agree with that. Again, I have pointed out to the transverse nature of electromagnetic radiation, but one can also postulate a longitudinal scalar wave. And again, this is sort of something that maybe has come out of Wesley's original work some years ago. So possibly you've only been looking at transverse electromagnetic waves rather than those plus longitudinal electrodynamic waves, John. Would that be fair to say?
No, I think I'm looking at longitudinal waves more than transverse.
So you have been looking at longitudinal waves?
I've been thinking of waves in the plenum as being longitudinal.
Because the longitudinal waves that I've been looking at don't really have a magnetic component. They're really relate to the electrostatic potential only, and not the magnetic vector potential as well.
No, I understand that, but suppose you, instead of saying electrostatic, you say that they are magnets moving, that they are groups of magnets moving. And the group is the longitudinal wave, just like water in the water, not on the water. Transverse waves are found on surfaces, such as the surface of water. And I don't know, that just doesn't seem to be the way things seem to work in terms of the plenum and Hodge. They're all longitudinal waves.
Okay. And maybe almost the last point, unless anybody has some pressing issue after I say this. Again, I probably adverted to this before, but I find it quite intriguing that you don't equate the magnetism occasioned by an electromagnetic field with that occasioned by a permanent magnetic field. And if that's so, I suppose you would counter a lot of the work on electromagnetic induction that has been done since Faraday's time, because you're saying they're sort of different phenomena. They shouldn't be confused. Would that be fair statement?
That's correct. The experiments I had, the first set of experiments was with permanent magnets. And they showed the asymmetry. I think it was the third experiment I did or something like that with electromagnets. And the electromagnets do not show the asymmetry that permanent magnets show. So they're different. But a permanent electromagnet is a solenoid. And if you think of each of these wires emitting little magnets, that's what's going on. And that's why it's not asymmetric. So electromagnetic magnets are not electro at all. They're magnets, producing little magnets. And that was one of the experiments. Remember where I had a big coil around a coffee can, and looked at the magnetic field at the bottom of it.
Right. There's just some further conversation about, not accepting Maxwell's prediction of electromagnetic waves and so on. But and Cornella says that John, like himself, probably does not consider longitudinal waves to be electromagnetic as they are not polarized. That's another matter. Okay, well, unless anybody has any final point to make, either from the green room or maybe this is a positive response from Cornelis. Finally, he says, "I agree with the need for Hodge in the plenum." So that's a positive support of your ideas, John. Okay, so as usual, I'd like to give you a few minutes if you want to say anything further. Now, you've probably said it all. You don't have to. Maybe that's all, and you'll allow me to summarize and complete the session. But just in case you want to say anything, John, also in response to maybe any of the questions or comments that have been made, Harry's very great points or Franklin's very great points, contentious points and so on.
Well, the STOE is a totally new paradigm shift. And we start with different fundamentals and we go forward. So when you start talking about things the way standard physics accepts it, you're not talking about a STOE. You're talking about something that's incommensurable with the STOE. And that is, of course, a lot of the difficulty we're having here. Perhaps it's my problem in that how do I explain these things as being totally different? But I submit that through these some five videos, going back into February, that the STOE is obeying Thomas Kuhn's idea of what represents a paradigm shift in physics. It is accurate. You've seen that because I compare it to measured data. I'm comparing to problems of standard physics, such as asymmetric rotation curves and the like. It's broad. It goes from cosmology down to interference experiments. It's simple. I mean, good God, there are two things in the universe, STOE, Hodge, and plenum, and there's only one force that emerges to all other forces. I think it's fruitful because many of these experiments have actually made predictions before the data was found. In the Pioneer anomaly, somewhat in cosmology, and certainly these experiments I've run were triggered by the STOE, and we end up rejecting a lot of what standard physics accepts as standard, such as Biot-Savart law, and I know Ian is going to kind of not like me for it, but also Ampere's law. So anyway, thanks for having me, Ian.
Well, thank you very much. I'll just get ready to make the official conclusion, because I see the discussions are still coming in. Well, certainly I found this paradigm fascinating. It's another way of looking at things, and I think we should give it due consideration without blindly accepting it or thinking that is the best way to investigate these physical problems. The one good thing is it's got us talking, and I can see the comments are still coming in. And even when we become very controversial, I have absolutely no problem with that at all. In fact, I consider it a healthy response. If everybody's just mum and doesn't really raise any fundamental questions, well, then there's probably nothing in the lecture. But once the lecture has got us to become controversial, I think that's a very positive result. So John has given us the benefit of very considerable work that he's done, actually, over the last 3 sessions. And the videos have been excellent. I do apologize for today, and I actually regret that we don't have the audio recorded for all time, which is what we have on the YouTube recordings of these. But anyway, I think at least from the analytical point, we do have the audio, so it's for maybe the majority of that video we actually have the audio, and there are references where we can find these anyway permanently on YouTube with the audio as well as the text. So as I did say, I think I've said this more than once, that John is continuing his work, and he's given us talks on cosmology and on the Pioneer anomaly and on the 9th planet and all that. And now today he's given us a panoply of various other problems which can be solved or are solved or have to be solved. And, the continuity of working in these areas will probably bear some fruit. So maybe towards the end of this year, we'll be able to address the questions again that STOE has raised and perhaps look at some of them in fuller detail. So thank you very much, everybody, for questions. I'm sorry again if we didn't get to every single question, and if any more precise question has not been addressed, well, they can always be submitted to us and we can deal with them subsequently. Similarly, I'd like to thank all of you in the green room, for strong points or for posing questions or for comparisons with other ideas. And thank you, Franklin, for your assistance today in making my task a bit easier. And finally, last but not least, by any means, I'd like to thank John, not only for today's presentation, but for the previous 2, and for having given us something that Vladimir has started by maybe giving a series of lectures where we can put them together and get a complete idea of what he's been doing in the scalar theory of everything. Those videos were actually very professional, so we could just play them without any further ado, if it hadn't been for my error of not including the audio in the first part of today's. So thank you very much, John. I look forward to not silence, but to a continuity of these ideas, even by emails or by other communications, and then further considerations of some of these fundamental questions we've been looking at. So thank you all very much again. Thank you, John, and I'll wish you all, wherever you are in the world, a very good day. Good day.